I'm going to spend a little time now in these next couple of videos talking about some very special vectors and kind of try to tie them all in together in a bit. So be a little bit patient. We're going to learn about a couple of vectors, and it may seem like, what the heck are they for? Well, we'll tie these in all together here shortly. This first one, we're going to talk about the normal and binomial vectors, but this very first one I want to talk about here. Let's take a look at a point on a smooth curve that's defined by the vector r of t. Now, there's an infinite number of orthogonal vectors in R3. In particular, right now, we're actually interested in what's referred to as the principal unit normal vector. So let's take a look at this thing, figure out how it's defined, and then, like I said, in another video too, we'll tie it all in together and see what's going on here, or why this is actually kind of important. Now, any point where kappa is non-zero, remember kappa is the curvature, we can define the principal unit normal vector as n of t equals t prime of t over the magnitude of t prime of t. Now let's think about this for a second. This is t prime of t. This is the first derivative of the unit tangent vector at some specific point divided by the magnitude of that unit tangent vector. So we end up with a vector. Matter of fact, it's a unit vector because it's the unit tangent vector is what it actually is. And notation-wise, sometimes you may see this with a hat over it. It's not at all uncommon to represent any unit vector with a hat over it. Different textbooks, different mathematicians use slightly different notation, but this is a somewhat common notation to represent a unit vector to begin with, this little hat thing here. Okay, now, this principal unit normal vector is in fact orthogonal to the tangent vector, the unit tangent vector. Remember the unit tangent vector, t of t equals r of t over, r prime of t over the magnitude of r prime of t. Now, these two guys are actually orthogonal to each other, although it may not be so obvious. Now, let me kind of show you why, or justify why. Since this is a unit vector, the magnitude is going to be 1. Therefore, if I take a look at t dot t, the unit tangent vector dot the unit tangent vector, this is going to be equal to the magnitude of the unit tangent vector squared, which is of course 1 squared, or which is 1. Therefore, I can say that d dt, take the derivative of t dot t, is going to be equal to d dt of 1, which is of course 0. So the dot product is 0. But the dot product, the derivative of the dot product, I'm sorry, I said the dot product is 0. That's not true. The derivative of the dot product is going to be 0. But the derivative of the dot product I could write as t prime dot t plus t dot t prime, and that is supposed to be, that is equal to 0. This is just rewriting this derivative. So that then implies that, see, these two are actually the same. 2 times t dot t prime equals 0, which obviously can only happen if t dot t prime equals 0. Therefore, since the dot product is a 0, therefore t and t prime are, in fact, orthogonal. Okay, so let's just discuss this idea a little bit more here. Now, we know that t is a unit vector, obviously. This is the unit tangent vector. And obviously, t prime is the first derivative. But there's no guarantee that t prime is a unit vector. I mean, there's no reason to even suspect that t prime is a unit vector. Because of that, we want to make t prime into the unit vector. And that's really all this principal unit normal vector is. This principal unit normal vector is really nothing more than taking the taking the tangent vector and turning it into, or the derivative of the tangent vector, and turning it into a normal vector. So that's why we take a look at, or we define it as t prime of t over the magnitude of t prime of t. So this n of t is in fact a unit vector. It is orthogonal to the unit tangent vector. I guess we could remind you that this is, again, that this is r prime of t over the magnitude of r prime of t. And a really important property of n and t is that it always points inward in the direction of curvature. And again, it's orthogonal to the unit tangent vector. So if I have a curve, let me see here, if I draw something like this. So here, clearly, my curvature is in this direction. So n of t would be a unit vector pointing inward in the direction of the curvature that's orthogonal to the unit tangent vector. So over here, my unit tangent vector would be like this. And of course, orthogonal pointing in the direction of the curvature would be here. Now, somewhere around here, let's say right about there, is an inflection point. I have a unit tangent vector. That still exists. However, what's the curvature? Let's go ahead and take a look at, we looked at this a little bit earlier, look at the curvature of r of x cubed. We parameterize as x cubed. Let's go ahead and take this vector and actually find the principal unit normal vector and see what happens to it when x equals 0. So we need some pieces here, so let's start looking for these pieces. Okay, there's r of x. Now r prime of x is going to equal the vector 1, 3x squared. The magnitude of r prime of x is going to be the square root of, I'm going to write it as 1 plus 9x to the 4th. I squared these components to the 1/2. So what I'm looking for is the unit tangent vector. So the unit tangent vector is going to be r prime of x over the magnitude of r prime of x. So that's going to be 1 over 1 plus 9x to the 4th to the 1/2 times the vector 1, 3x squared. Okay, so now I need the derivative of the unit tangent vector. So t prime of x, I'm going to write this out like I did in an earlier example. I'm going to make this ddx of 1 plus 9x to the 4th to the 1/2. Take the derivative of this times this vector 1, 3x squared plus 1 plus 9x to the 4th. Oops, this is negative 1/2, sorry. Negative 1/2 times ddx of this vector 1, 3x squared. So this is going to be negative 1/2 times, I'm going to go ahead and take the derivative of the inside right now. This is 36x cubed times 1 plus 9x to the 4th to negative 3/2. And I need to multiply by this vector. Plus, this is going to stay 1 plus 9x to the 4th to the negative 1/2 times the derivative of this vector, which will be 0, 6x. Now, I'm going to do some simplification here. This is going to be 18. So this is going to equal, if I factor this out, I will have 1 plus 9x to the 4th. This is going to do it right in fractional form. To the 3/2 times, and I will distribute this negative 18 into here, times the vector negative 18 x cubed, can't forget that. And then I'm going to have a negative, what? See, where am I? Negative 54 x to the 5th. Takes care of that vector. And this is going to be plus the vector, well, this was factored out, so this is actually going to be to the first power. So this would be to the vector, this would be 0, and then 6 times this. This would be 6x plus 54x to the 5th. So now I can add these. I'll have 1 over 1 plus 9x to the 4th to the 3/2 times the vector. I'm going to have a negative 18x cubed. This is going to go away this, and 6x. And I'm going to factor out a 6 to make things a little bit easier to work with. And when I do, I'll have 6 over 1 plus 9x to the 4th to the 3/2 times the vector negative 3x cubed 2x. See, that's going to be a lot easier to find the magnitude of. Okay, so I need the magnitude of this because where I'm heading to is, remember, n of x is going to be t prime of x over the magnitude of t prime of x. So this is going to be, see, t prime of x will give me 6 over 1 plus 9x to the 4th to the 3/2 times this vector, negative 3x cubed 2x, divided by the magnitude of this. So I'm going to have another 6 over 1 plus 9x to the 4th to the 3/2, which is nice because that's just going to cancel out, times whereby the magnitude of this. So this is going to be, if I square this, I'm going to have 9x to the 6th plus 4x squared. And this is to the all to the 1/2. So there's my principal unit normal vector. I'm going to rewrite it one more time. Negative 3x cubed 2x over 9x to the 6th plus 4x squared out of the 1/2. Now, my point here is when I take a look at this function x cubed, because actually I could make that a little bit bigger. What I'm talking about here is when x equals 0. And we already said that the curvature is 0 here. So what's going to happen when I put in x equals 0? When I put in x equals 0, I get the 0 vector divided by something that's undefined. So the principal unit normal vector doesn't exist. If there's some kind of constant here, it would still be the unit, or it would be the 0 vector. So it doesn't exist, which makes sense. Which way would it point when there's no curvature? Because one of the nice principles of this particular unit vector is that it points into the direction of the curvature. So logically, I mean intuitively, you would think, gosh, which way do I point? Because there is no curvature here.